Hello everyone, I'm Sebastian Y, and this is Managerial Economics. In this video, we're going to talk about how to do hypothesis tests for regressions. Broadly speaking, a hypothesis test is a statistical tool that we use to test whether a particular belief about a population is backed up by the estimates from the data sample. Using samples to make claims about a population is called inference. Any kind of inference is first going to require that we have consistent estimates, which we talked about in the previous video. The second thing that we need is to know the distribution of the estimates, and that's what we're going to talk about first. To think about the distribution of the estimates, we are going to use the central limit theorem, or the CLT. We denote our estimates in a regression as beta j hat, where j could be 0, 1, 2, all the way up to k. Each estimate that we get is normally distributed with a mean of beta j and a standard deviation of sigma j. The CLT states that our estimates have this kind of distribution if the sample size, which we denote n, is sufficiently large. A good rule of thumb for how large is large enough is n is greater than 30 times k plus 1. The idea behind this is that we need at least 30 observations per parameter we are estimating. Remember that our regression equation has k variables in it, and each one of those has a coefficient, a beta j, next to it, but we also have that intercept term, beta naught, that does not have any variable next to it. So we are estimating in the regression k plus 1 parameters. The fact that our estimates have a probability distribution at all suggests that they are random in some way. The reason why our estimates are random is that our sample is random. If we were to go to the population and take another sample, randomly selected, we would get different members of the population in our new sample, and the estimates that we would get would be a little bit different from the first time. To show this, I'm going to go back to our Excel file. We previously ran a regression using data 1. In that regression, we got the results right here, the intercept of 4,279 and slope of negative 9.5. We're now going to go over to the tab Data 2. This looks very similar to Data 1, it's just a new sample from the exact same DGP that I pulled the Data 1 sample from. If you want to actually go and look at the DGP, you can go to the next tab right here. If you want, you could even use this DGP to generate another sample of your own. But let's just go back to Data 2. I'm going to run a regression using this data by going to Data Analysis, Regression. For the Y range, I'm going to select the quantity column, Control-Shift-Down to select the entire thing, and for the X range, I'm going to select the price. Notice that for both of these, I am including the top line, so I'm going to click Labels, and then run the regression. Zooming in on our coefficient estimates, you can see these numbers are reasonably close to the ones we got earlier, but they're not the same. Here we have 4,090 for the intercept compared to 4,279. And then we have for our price coefficient estimate negative 8.1 as opposed to negative 9.5. They're all in the same ballpark, but not the same. If we were to go back to that DGP and run another regression with a new sample, we would get a third set of estimates that again would probably be reasonably close to the ones we got, but again would be a little bit different. What the central limit theorem says is that if we were to keep doing that over and over and over and make a histogram of our results, we would get a normal distribution. And that histogram would look something like that classic bell curve shape associated with the normal distribution. Since that distribution has a mean of beta j, that would be the middle of this distribution, and sigma j would tell us how spread out this distribution is. If we want to use this distribution, though, we have a big problem. We're trying to use beta and sigma, which are population parameters, to talk about the distribution of our estimate. Unfortunately, we do not know what beta and sigma are. If we knew what beta was, we wouldn't need to estimate it with beta hat to begin with. So we're going to have to replace these with something else. In particular, we are going to replace sigma, the standard deviation of this distribution, with a statistic from the sample called the standard error, or SE, of beta j hat. There is a mathematical formula to calculate the standard error, but it's quite complicated and I don't feel adds a lot to the discussion here. So I want you to understand what the standard error means and what it does, but we are going to let Excel calculate it for us. The standard error is the estimate of the standard deviation of beta hat. In effect, it is a measure of how precise our estimates are. The higher the standard error, the less precise the estimate. The lower the standard error, the more precise the estimate. In a practical sense, this means that if we were to do those repeated samples, like I was talking about earlier, a low standard error would indicate that the estimates that we would get sample to sample would be all relatively close to each other. A high standard error indicates a lot of randomness in the estimates. So if we were to repeatedly sample, the estimates would be all over the place. This means if we have a low standard error, we can be more confident about our estimate using a single sample. In general, the standard error goes down as sample size goes up. This is why large samples are always better for making predictions. They won't solve all of our problems, which we'll talk about later on, but they are always helpful. Back over here in Excel, we're going to look at that original regression we did with data 1. The second column of the regression table shows the standard errors. In this regression, we estimated that the intercept is 4,279, and the standard error of that estimate is 284. Same thing for the price coefficient. We estimated that to be negative 9.5, and the standard error of that estimate is 1.38. Standard errors on their own don't mean a whole lot. We wouldn't necessarily say that just because this first standard error is a lot bigger than the second one, that it's a lot more imprecise, because we have to take into account that the estimate is a lot bigger. An estimate that just tends to be a big number is naturally going to have a higher standard error than an estimate that is a low number. Now that we've established the sampling distribution of beta hat, we are now going to talk about hypothesis testing. There are 4 main steps to hypothesis testing, and we're going to go through all of them. Number 1 is state the null and alternative hypothesis. The null hypothesis is denoted H0. H0 is a claim about one of our parameters, beta j. Could be beta 0, could be beta 1, beta 2, and so on. Remember that this is a population parameter, so H0 is making a claim about the population. We state a null hypothesis as beta j equals c, and c is just a number. Could be 10, 20, whatever. So the null hypothesis is simply claiming one of our parameters is equal to some number. The alternative hypothesis is denoted H1, and that is simply that the null hypothesis is not true. So beta j does not equal c. The null hypothesis is the position that we are trying to test using the hypothesis test. Ultimately, what we're going to try to do with the hypothesis test is determine whether the evidence that we have is strong enough to throw out that initial null hypothesis or not. The next step is to calculate a test statistic. The test statistic we are going to use is called the Tstat. We calculate the Tstat as beta j hat, that's our estimate from the sample, minus c, divided by the standard error of beta j hat. The t statistic has a particular statistical distribution called the t distribution. Specifically, it has a t distribution with n minus k minus 1 degrees of freedom. With a sufficiently large sample size, we can apply the central limit theorem, and the distinction between the t distribution and a normal distribution is relatively trivial. If you want to do this with the highest amount of formal correctness, you're going to want to use the t distribution. we are just going to use the normal approximation here. The normal distribution has a very convenient property where you can subtract off a mean and you can multiply by standard deviations to express all normal distributions in terms of the standard normal distribution. This is very convenient because then we only have to learn one distribution and then we can apply it to all these different situations. So by dividing by the standard error and subtracting off the null hypothesized value, the t-statistic has a standard normal distribution as long as the sample size is sufficiently large, which we say as normal 0, 1. A standard normal is just a normal distribution with a mean of 0 and a standard deviation of 1. We're going to use this fact in a few minutes. Step 3 is decide on a confidence level. The whole point of the hypothesis test is to see if the evidence that we have from the sample is sufficient to reject the null hypothesis. The confidence level asks us, how sure do we need to be? What we're going to do is assume that the null hypothesis is true, and with that assumption in mind, think about how unlikely it is that we got the result that we did. Are the results that we have far enough away from what we would expect with the null to come to the conclusion that the null was in fact incorrect? The three most commonly used confidence levels are 90%, 95%, and 99%. For a 90% confident rejection, we need the result that we got to be less than 10% likely to happen if the null were true. For 95%, it's 5% chance, and for 99%, we need only a 1% chance. The higher the confidence level, the stronger the rejection, but the less likely we're going to get that rejection. It's entirely up to the analyst about how stringent the confidence level needs to be. The fourth and final step is to compare the test statistic, that's our Tstat, with the critical values that correspond with our chosen confidence level. This is where the standard normal distribution is so useful to us because we only need to learn the critical values from that one distribution and we can use them for everything. For 90% confidence, the critical value is 1.65. For 95%, it's 1.96. And for 99%, it is 2.58. Once we have chosen our confidence level and corresponding critical value, we're going to compare the absolute value of the Tstat, which can be positive or negative. It doesn't really matter because we're just taking the absolute value, and compare that with the critical value we picked. If the absolute value of the t-statistic exceeds the critical value, which is going to be one of these, then we reject the null hypothesis. If the absolute value of the t-statistic does not exceed the critical value, then we fail to reject. We always want to use this language, fail to reject, because a failure to reject the null is not a confirmation of the null. It just means that we did not have enough evidence to reject the null. Does not confirm that the null is true. A rejection of the null hypothesis means that if the null were true, the result that we got from the data would be highly unlikely. For a 90% confident rejection, that means less than 10% likely. For 95% confidence, that means less than 5% likely, and for 99% confidence, it means less than 1% likely. A failure to reject the null means that the chance of the outcome that we got happening is larger than that number. Let's return to our demand equation for an example. Recall that we have qxd equals beta naught plus beta 1 px plus epsilon. We're going to go through an example hypothesis test. Suppose our hypothesis is that the slope of the demand function is -7. We write out our null hypothesis, h naught, as beta 1 equals -7. This just means that our starting belief is that the population parameter is -7. The alternative hypothesis is that beta 1 does not equal 7. The next step is to calculate the t-statistic. The t-statistic is going to be beta 1 hat, that's our estimate from the regression, minus c divided by the standard error of beta 1 hat. Looking at our regression output that we got in Excel, I'm going to plug these numbers in. Beta 1 was negative 9.517. C here is our hypothesized value, so we're going to take minus negative 7, and then divide that by the standard error, which also comes from our regression output, and that was 1.389. I'm not going to just punch these numbers into a calculator because I want to avoid rounding. That means we're going to go back over to Excel to actually do the calculation using cell references. Back over here in Excel, let's calculate our t-statistic. So we're going to make a formula, equals, and for the numerator, we take our beta 1 hat, and then subtract negative 7. The negatives cancel out, so we just get plus 7. And then we divide that by our standard error, which is this one right here. And what we get is negative 1.813. The next step is to compare this t-stat with our the next step is to compare this t-stat with our critical values. Remember that our critical values are for 90%, 1.65, 95%, 1.96, and for 99%, we have 2.58. We take the absolute value of the t-statistic and compare it with each of these. 1.65 is less than 1.813, so that's a rejection. 1.96 is greater than 1.813, so here we fail to reject. 2.58 is also bigger than 1.183, so we also fail to reject. Notice that if we reject at any given confidence level, we can also always reject at all the lower confidence levels. But if we fail to reject, we also fail to reject at all the higher confidence levels. So we would say here that we reject the null hypothesis with 90% confidence, but we fail to reject with 95 or 99% confidence. To illustrate this a bit further, let's draw a graph. Using the central limit theorem, we have our t-statistic normally distributed according to the standard normal distribution. So it has a mean of 0 and a standard deviation of 1. The area under the curve represents the total probability. So the area under the entire curve adds up to 1. Let's take a look at the critical values and what they mean. If we look at 2.58 and negative 2.58, all of the area on the outside of those critical values adds up to 1%. And so that corresponds with the 99% confidence level. Since the normal distribution is symmetric, to add up to 1%, we would have 0.5% on each tail. We can do the same thing for 1.96, negative on that side and positive on this side. If we take all the area on the outside of 1.96, these areas all add up to 5%, corresponding with a 95% confidence level. So that means that the blue and green areas on each side are each 2.5%. And finally, we can take a look at our 90% critical values, which is 1.65 and negative 1.65 over here. The probabilities in the tails there add up to 10%. So this means the green, purple, and blue areas on each side add up to 5%. We can then put our t-statistic on this graph. What we got was 1.813, so that's somewhere in between 1.65 and 1.96. we could put that on either side. If we look at the area under the curve to the left of negative 1.813 and to the right of positive 1.813, that adds up to greater than 5%, but less than 10%. And so this is going to correspond with rejecting at 90%, but failing to reject at 95%. The last thing to talk about in this video is the concept of statistical significance. Statistical significance means that we can reject the null hypothesis that a certain parameter is 0. For this test, then, the alternative will be that beta j is not equal to 0. Calculating the Tstat for a statistical significance test will be beta j hat minus 0 divided by the standard error of beta j hat. This looks exactly the same as a normal hypothesis test. It's just the hypothesis is that the parameter is 0. We don't have to write that 0, so we can just take beta hat j divided by the standard error. This is probably the most common hypothesis test that you see in economics because it asks a very fundamental question. Does variable xj have any relationship at all with the dependent variable y? As with any hypothesis test, we need to specify what the confidence level is. So it does not have any meaning to say that something is statistically significant without saying what the confidence level is. So for example, you could say something is statistically significant with 90% confidence. Let's look at an example of this in Excel. We're going to look at the statistical significance for price in our regression. Calculating the Tstat, we take our estimate, beta 1 hat, subtract the null hypothesis value, which is just 0 in this case, so we don't need to write anything, then divide that by the standard error. What we get here, negative 6.85. This is much bigger than any of our classic critical values, 1.65, 1.96, and 2.58, so this is a clear rejection of the null at all three of those confidence levels. This suggests that our variable price has a highly statistically significant relationship with the quantity. Because this is the most common kind of hypothesis test, the regression output will actually give you the t-statistic right there in the table. This means these numbers have the relationship beta hat divided by standard error equals the t-stat that you see there. So if you want to do a test for statistical significance, you don't even have to calculate the Tstat yourself, you can just pull it from the table. But if you want to do it, any other kind of hypothesis test, like the one we did before, then you're going to have to actually calculate the Tstat. That is how we do a hypothesis test using a regression. In the next video, we're going to move on to some nonlinear functional forms.